Now I want to think a bit more about viscosity and irreversibility, disordered motion and ordered motion, and this is more of a descriptive little note rather than anything more formal. Let's zoom in on a gas, and we know we've got lots of molecules and they're all zooming around at lots of different speeds in lots of different directions, and we take a sort of clump of those and we average over those to get a sort of an average velocity. Note there I've said velocity, it has a vector, and therefore would be of the ordered motion. I say ordered in that the whole clump, for example, is moving in that direction at some velocity v. That's what I mean by the velocity of the ordered motion. And if you look at the kinetic energy of the ordered motion, that would be related to, well, you sort of get a half rho, because it's per unit volume, say, v squared, where v would be the velocity vector. On the other hand, there's a lot of extra motion in there that we've missed out, because these molecules are moving around so quickly. There's an enormous amount of energy in disordered motion. So we can look at the kinetic energy of the disordered motion. This is measured by the speeds of each molecule, and note the difference between the speeds and the velocity. The speeds is just how fast they're moving around, and the energy of that is really measured by temperature. Now in thermodynamics you come across the steady flow energy equation, which says that if you have going into here no heat flow and no work being done on this gas, then the enthalpy plus a half v squared is equal to a constant. Now let's imagine we're looking, for the sake of this argument, at something with constant specific heat capacity. The enthalpy can be written as Cpt plus a half v squared, then, for the velocity of the ordered motion, is equal to constant. And let's look at what these terms are. The Cpt here is essentially, if you like, the kinetic energy of the disordered motion. Whereas the half v squared here, by the way that's per unit mass, is the kinetic energy of the ordered motion. And it's equal to a constant if we're not adding any heat and not doing any work on that system. So you can see there's a sort of physical explanation there for the terms in the steady flow energy equation. And you can also see why. If the velocity of the ordered motion goes down, the half v squared term reduces, then the temperature goes up, which is something that you'll see, or you will have seen, in thermodynamics. So let's imagine two layers of fluid, one of them going at velocity v1 with mass m, and the other one going with velocity v2, again with mass m. Let's think about the kinetic energy of the ordered motion here. It's just a half m v1 squared for the top one plus v2 squared for the bottom one. That's of the ordered bulk motion. Now imagine that they mix, and that at the end you've got one quantity of mass 2m that's got an average velocity, a velocity now of v1 plus v2 over 2. So the kinetic energy of ordered motion here is a half times 2m times v1 plus v2 squared over 2 squared, which is 4. So let's think of this kinetically, another term in terms of atoms and molecules. We can imagine all the molecules that are zooming around in here with an average bulk velocity of v1. We've got all the molecules zooming around in this bit of fluid that have an average or bulk velocity of v2. Here they're zooming around, as we'll find out, a little bit faster than they were before, having collided with each other, but they've exchanged their bulk velocity to average it out to v1 plus v2 over 2. So let's look at the change in the kinetic energy of the ordered motion. Now this is equal to a half m v1 squared plus v2 squared, which is what it was before, minus a half times 2m v1 plus v2 squared over 4. Now you can do this sum and you'll find that that's equal to a quarter m v1 minus v2 squared. Now because of the squared term here, it's always positive. You'll notice that little check, when delta v is equal to 0, there's no loss in kinetic energy of ordered motion, and as v1 minus v2, or delta v, increases, we get an increased loss of kinetic energy of ordered motion. Now, where's that gone? Well, of course, we know from the steady flow energy equation, or we know from just thinking about this physically, it can't have gone, the molecules collide off each other elastically, so it hasn't disappeared, it's gone to disordered motion. In other words, the temperature has increased. So we can get that argument by thinking about the molecules if we want to. But if you were to talk in terms of a continuum, you'd say that this was a viscous process. In other words, it's really due to the fluid's viscosity and the fact that these molecules exchange momentum by bumping into each other. That's in the continuum model we talk about that being a viscous process, has led to an increase in disorder, or more specifically the energy of the disordered motion, and an increase in temperature. Now, a physicist would say that because the degree of disorder has increased, you've got an increase in entropy, and therefore it's irreversible. And so you get this idea that when you've got molecular motion and you've got a velocity gradient, you get an irreversible process, and that this, in a continuum sense, is a viscous process. So viscosity, this is what I wanted to get to, is essentially, you can think of it as causing irreversibility. Now these are only sort of, this is for physical understanding I've done this, it's not enormously rigorous, but I think it gives you a good understanding of the relationship between molecular motion, velocity gradients, viscosity, irreversibility, and the steady flow energy equation, disordered motion and ordered motion.